Welcome back to Larry's Classroom. We're going to continue our study of mathematics for electricity and electronics. And we're going to talk a little bit about precision and accuracy today. What is precision and accuracy? Well, virtually all numbers we use, except for numbers where we count something in our world, have a certain amount of approximation to them. Now you could count Legos and put them into a jar and know exactly, precisely, with no margin of error how many there were. You could count all of the transistors in a transistor radio by looking at the schematic. But our other numbers, which are more or less what we call analog numbers, are never exact. They always have some degree of approximation in them. Say you take a voltmeter and you read the voltage of a battery and you find 12 volts. Is that battery 12 volts output with no margin of error whatsoever? Say you get a more precise voltmeter to read a little bit closer and you read that same battery. Now you see 12.6 volts. Or you find an even more precise, more accurate voltmeter, and you have 12.63 volts. What this shows us is that our margin of error is never zero. So we have to think about things like significant figures or significant digits. If we got a number, let's do this. Let's say 1073. Always digits 1 through 9 are significant. And this is what we call a whole number. We have no fractional part. Zeros are significant when they are not the first number and not the last number in a whole number. If we see a number like this, 1130, this zero would not normally be considered a significant digit. This would be what we consider a three significant digit number. This one up here, because this zero was significant, because it's not the first or the last, would be a 4 significant digit number. Now, if we have reason when we're providing this number to know that this is a significant digit, we would put a bar over the top of it to indicate that zero is significant, even though it's at the end of a whole number, at the right end of it. Now, if we have a number like this, 01320, this is a whole number. This is a leading zero, which doesn't do anything for the value, so we wouldn't consider that significant. This trailing zero on this whole number would not be considered significant unless we put the bar over it. When we were making that measurement, we had some reason to know something about that number. We would add the bar. That would make it a 4 significant digits. Or without the bar, it would be 3 significant digits. In addition, on the fractional part, the decimal part, let's not put a whole number on this, 0.0130. This zero is not significant. It's just to help you offset your eye locate the decimal point. And this leading zero in the fractional portion, or the decimal portion, is not significant. Normally, we do consider this a significant digit, which is a trailing zero in the fractional decimal portion of the number. If that zero is not significant, we leave it off. So if you see it there, that tells you that whoever wrote that number had a reason to believe that was a significant digit. So we're going to think about, look at a few examples and think about how many significant digits they are. Let's take this number, 0.0032. Well, this one over here in the whole number portion is not significant. These two leading zeros in the decimal or fractional portion are not significant, but these two are. So this is two significant digits. Two significant digits to that number. Take another one here, 2.046. Well, there are no zeros ahead of to the left of the whole number portion, so this 2 will be the first significant digit. This 0 is neither the leftmost or the rightmost. It's not the leftmost or the rightmost of the whole number part, but if it's in the fractional part, it's not the rightmost of the fractional part, so that's a significant digit. And numbers 1 through 9 are always significant, as we said a few minutes ago. We'll put that up here. So this is going to be 4 significant digits. We have 4 significant digits for this number. How about this guy here? 6.70. Well, we got no zeros to the left of the whole number portion, so we know that's significant. The 7 is always significant. They fall into the 1 and the 9. The 0 on the trailing end or the rightmost end of the decimal portion is significant. Well, let's quickly kind of talk about 1, 2, 3. Let's kind of talk about why. Well, when we talk about rounding, we'll talk about why. We'll get another number here. 0.702. Numbers 1 through 9 are always digits 1 through 9 are always significant. There's 7 and 2; those are significant. And 0, when it's not to the left of the decimal portion, or the last part of the whole number portion, is going to be significant too. So 1, 2, 3. So that's 3. For example, if we had 730 just 730. This is the rightmost edge of the whole number portion. It's not significant unless we tell it so. This 0 does not fall into the rightmost edge of the whole number portion, nor does it fall into a leading 0 like that on the whole number portion. So this is a significant digit, this 0. Do one more here. Here's a whole number. Nice one. 5. Now we've got a bar over that number. 0, when it's the rightmost portion of the whole number portion, is not a significant digit. And this one would not be either. But we've made a mark to tell the reader that this is a significant digit. So basically, we have the 5 that's always significant. We have the 0, which is sometimes significant, and this bar indicates that it is. The 0 here, rightmost edge of a whole number, not significant. So that's going to be 2 significant figures in that number. Another whole number. No leading zeros, don't need to worry about that. No trailing zeros, don't need to worry about that. 1 through 9 are always significant. 1, 3, 6. So we have 3 significant figures plus this 0 when it's when it's enclosed by other digits such as the 1 through 9, when it's bracketed or surrounded by non-zero digits, will be significant also. So we got 1, 2, 3, 4. We have 4 significant digits here. Okay, we're going to talk about rounding decimals, the numbers that have a portion to the right of the decimal point. Rounding decimals. So, if the number to the right of the rounded number is 0 through 4, or we could say less than 5, we do not change the last rounded digit. And we're going to put another rule up there. If the number to the right of the rounded number is 5 through 9, or we could say greater than or equal to 5, or equal to 5, we increase the rounded number by 1. Or you might have heard said, if that number to the right of the number you're rounding is 5 or greater, we round up. Well, that's increased by 1. That's rounding up. Let's look at a couple of fractions. 2/9. That is equal to 0.2222. Repeating. In this case, we put a bar over. That means that repeats indefinitely. We could write that as 0.2. When you put that bar over the last portion, it means the portion the bar is over. When you're talking about the decimal fraction part, that means it repeats indefinitely. Well, if we were to round this to 2 places, we want to end it off here. We want to we want the last number to be the 2, so we'll say 2/9, and now we're going to use this approximately equal symbol because we've rounded this. 2 significant digits. Now, this is the rounded number. We got to make a decision. Are we going to make that be a 2? Or are we going to round it up to a 3? Well, the next number is a 2. If the number to the right of the rounded number is 0 to 4 or less than 5, we don't change the round number. Don't change rounded number. I forgot to put that up there. So by following that rule, we will see the number to the right of here was a number from 0 to 5, or 0 to 4, which was less than 5, so we don't change that number, so there we go. Let's do another example here with a fraction. I'm going to try to do these examples and try to make sure you understand why we're doing each of them. Let's do 2/3. Now if you divide out 2/3 on your calculator or by hand, either one, you'll find out it goes 0.0666 and repeats indefinitely. So if we want to round that to 2 places, now we use approximation. It's kind of like a wavy equal sign, approximately equal to, instead of exactly equal to. Well, we're going to 2 places, so the first place nothing changes. So the number we're rounding is the second place. That is a 6. What is to the right of the 6? It's a 6. If we look at, if the number to the right of the rounded number is 5 through 9, or greater or equal to 5, well 6 is 5 through 9, or greater or equal to 5, then we increase the rounded number by 1, or we round up. So we increase the 6 to a 7 because we had a number here that was greater than or equal to 5, which happened to be 6. And if you punch this in your calculator, if you go 2 divided by 3 equal, you will probably see whatever the limit of your calculator is, 6, 6, 6, 6, 6, and a 7 on the end. Because it follows this rule and rounds it up for you. I'm going to keep these rules up here for right now as we do some more examples, because we're going to refer to them as we do each one. Now, we're going to take the number 4.527. 527, not 2. Oh wait, it's 527. Okay, I've got to finish right. 4.527. First, we're going to round this to 1 decimal place, or to 1 significant digit. Not one significant. Well, 1 significant digit. We got to take this first one, which is a 4. We got to look to the right of it. We see a 5. So I'm going to write right here to help us. 0 to 4, 5 to 9. We'll write that right there just so it's easy to spot. The 4, we go to the number, that's the digit we're rounding. We're rounding to 1 significant digit. Well, if we look at the 5, which is to the right of it, we see it's a 5 to 9 that says increase by 1. So we're going to rewrite this simply as 5. That's 4.527 rounded to 1 significant digit. Let's go to 2 significant digits. Well, 4.5 is going to go there, 4.5, right? Now, I don't want to write the 5 down yet. The 4 will go there. 5 is the one we're rounding. What is to the right of the 5? That's a 2. 0 to 4, we don't change anything, so that becomes 4.5. Now let's do to 3 significant digits. Well, we write the first 2 down. They're not going to change, are they? 4.5. Now the 2 is the one we're rounding. We look to the right of it, we see a 7. That falls in the 5 to 9 area. We increase it by 1, so that becomes 5. Instead of 2, we put down a 3. So we got 1 significant digit, 2 significant digits, 2, 3 significant digits. And we utilize these rounding rules to decide what to do with them. How about this one? Let's do another one here. 0.08236. Now we want to round that to 1 significant digit. Now remember, this leading 0 in this fractional portion, or the decimal portion of the number, is not a significant digit. So we're going to be rounding to this number. So we need to look over to the right of it We see it's a 2, which falls in the 0 to 4. We do nothing. So it's basically 0.08. We kept this first significant digit. We did not change it because the right of it was a 2. Now, what if we go to 2 significant digits with this thing? Well, we'll write down the first one. That ain't going to change. 0.08. Now we're looking at the 2. That's our second significant digit. What's to the right? It's a 3. We don't do anything. So that stays as 0.82. Let's go to 3 significant digits. We'll write down the first 2. There's the first one, the 8. The 2. Now we got to look at the 3. We've got to make a decision. Do we round up or do we keep it as is? Well, we make our decision by looking one digit to the right. We find a 6. That falls in the 5 to 9, which means we round up 1. So it becomes 0.824. We're going to do one more and then we're going to move on to the next section here. 6.999. We want to round that to one significant digit. Well, one significant digit, the first significant digit right here is 6. We got to make a decision what to do with that. We look to the right, we see the 9, so we round it up to a 7. So one significant digit, that's a 7. 2 significant digits, we got a 9. We look over here, see what to do. We round up because it's 5, 9, which makes that a 0, moves the 1 over. It becomes 7.0. Now, you'll notice these both look the same, but we have an extra significant digit. It rounded to 7, but this portion rounded to a 0, or 10 actually, but the 1 carried and made this a 7. But this shows we have more significant digits even though they look very much alike. And you're going to see the same thing here when we go to 3 significant digits. If we took the first 2, then the 9, that's what we're going to round. We'll look over here, it's a 9, so that rounds up to a 0. Carries the 1, that rounds up to a 0. Carries the 1, that becomes a 7. So here's 1, 2, and 3 significant digits. They all look like 7, but you see we have these trailing zeros after the decimal place that give us indication that this number has a more careful meaning than a more exact meaning. So we've been rounding decimal numbers, and we're going to kind of use a similar rules on whole numbers. If the number to the right of the rounded number is 0, change everything to the right to 0. So in this case, if we're looking at a rounded number, whole numbers, if the number to the right of the rounded number is 0 or less than 5, change all numbers to the right to 0. The right to 0. 0. Put that O with a slash to help indicate it's not an O. Okay. If the number to the right of the numbers 5 or 9, increase the rounded number by 1, then change the rest of the numbers to the right. All to the right of that point. Right. All to the right of the rounded number to 0. So we'll look at a few examples here, see if we can make some sense of this. We have this number, 4, 7, 5, 2. we want to round that to one significant figure. Well, the first number, that'll be, we'll be rounding this first significant figure in this number, which is a 4. We look to the right, we see that it's a 7, which is in the 5 to 9, which means we're going to increase the 4 by 1, change everything else to 0. So if we round to one significant figure, we're going to be increasing the 4 by 1 because of the 7 here, and everything else becomes a 0 to the right of that. That becomes 5,000. Now if we take the same number and we go to two significant figures, the 4 won't change. We're rounding the 7. Now what happens with the 7? We look to the right, we see it's a 5. And that tells us to increase it by 1, so we got 4, 8, and then everything after that becomes a 0. Now when we go to three significant figures, we got to look at this guy and see if it's going to, that's going to be the rounded number, 1, 2, 3. The third one's going to be the rounded number. We look to the right of it and decide what to do, increase or decrease. We don't do anything. So for three significant figures, it's 4, 7, 5, and then a 0 here, because after the rounded number on a whole number, everything to the right is 0. We just have to make a decision what to do with the rounded number based on these rules. Let's do one more here. 24,086. Round it to one significant figure. Well, there's the number we're going to round or not round. What's to the right of it? It's a 4. Falls into don't change anything. But now everything to the right of the rounded number is 0. So it's 2, 0, 0, 0. If we go to round to two significant digits, 1, 2, we've got to look at the 4, see what we're going to do. There's a 0, we don't change anything, and make zeros from there on. So for 2, the 4 doesn't change because of this rule. The next number falls in here, and then everything to the right is 0. So that becomes 24,000. And you can kind of see here that 20,000 is kind of close to 24,086. That's one significant figure. We get two significant figures, we're a lot closer, aren't we? These two numbers look a lot more alike. Now we're going to go one more, to the third. So we're interested, this is our rounded digit, it's a 0. We look to the right. Is it in the 0 to 4 or the 5 to 9? It's in the 5 to 9, which says we increase the rounded digit by 1. So the rounded digit, which was now a 0, becomes a 1. And everything else that is after that is 0. 24,100. So you see one significant digit kind of falls in the same ballpark. Two significant digits is a little bit closer. Three significant digits is even closer yet. But the rule is basically based on what number falls to the right, and that rule works for the decimal portion and the whole number portion, but we add zeros after the rounded digit to get the right place value for everything, for the whole number. We're going to do one more here. 9,999. We round that to one significant digit. Well, that means that's our rounding digit. We got to decide what to do based on what is to the right of it. There's a 9 to the right of it. That falls into the 5 or greater, which means we increase it by 1. Well, what's 1 more than 9? That's 10. So this single digit gets replaced by that. And now everything after that is going to be zeros. This guy was replaced by the 10. These two are going to become zeros. And I think you can probably see that the one significant digit, the number 1,000, is a decent representation of 999. Now what happens if we go to two significant digits? Kind of the same thing. we got to look at that second one. It's a 9. We go to the right, it's got to round up. So that 9 becomes a 10. If that 9 becomes a 10, we got to carry a 1. So we end up with another. And then everything to the right becomes a 0. So we end up with this kind of the same thing, but there's a difference. The 1,000, we rounded this second 9. You had a ripple effect to the left, which made it be 1,000. But we've rounded this to 2 significant digits, which tells us this guy, the first 0, is significant. So we put a line over that to indicate to the reader that that is a meaningful, significant digit. Now, if we take this same number and round it to 3, we're going to look at that third digit. Okay, I don't think we round that one up. I've written down that we should. Yeah, well, what's to the right of the 9? There's nothing. So basically the 9, it's a 0 over there if you went past the decimal place. So that rounded digit does not change. So 999 remains the same when we've rounded this to 3 significant digits. And you can see that that would be a little bit closer to the given number than 1,000. Now let's just say we had this number, 9999. That's almost 10,000. We round that to 1 significant digit. The 9 here tells us increase that, replace that with a 10. So we end up with 10,000. We go to 2 significant digits. Kind of works the same. We're rounded this one. We look over there. That increases this to 10. That carries over. So we end up with basically the same number. But now this 0 is significant. We go to 3 significant digits, kind of the same thing happens. The 9 rounds up because we have a 9 to the right of it, and that causes a carry and a carry. So it looks like 10,000, but we have, these zeros are both significant because that was our rounded digit. And we've got it rounded as close as you can represent it with that many numbers, that many digits. So, what do we got to talk about next here? We've got plenty. Okay. We've kind of discussed this. I'm going to go ahead and erase this. We just want to reinforce this so that we can't sort of get it more clear, more programmed, so we are not so likely to mess it up. Zeros at the beginning of a decimal number, not significant. Example here, 0.0050. These 2 zeros are not significant. This trailing 0 is. This actually has, we don't have to put a line over that because it's automatically, a trailing 0 is automatically significant when you actually write it down in a decimal. If it was not significant, you would choose not to write it down. And zeros between non-zero, any 2 non-zero digits, are significant. And we talked about this a little bit. 0.4080. This leading one is not significant. This one that's sandwiched between the 4 and the 8 is significant. And because it's a decimal, the 0 at the end is significant, or we wouldn't have written it down. And that's in the decimals now. Zeros at the end of a whole number are not significant unless there's a bar. Unless a bar is above them. Bar above. Example. 540. To write it like that, the 0 is not significant. But that would be 2 significant digits. If we put the bar over it, the 0 is significant. Now without the bar, this could be 541, 542, 543, or 544. Because we do not know, being we know this is 2 digits, we can assume that it was rounded from something to 2 significant digits, and any one of these numbers would round to 540 as 2 significant digits. Now this one over here, we know that that's a 0, that it wasn't rounded. It could be 540.1.0 actually. It could be 540.1. It could be 540.2, 540.3, 540.4. So that if there was a number added to the right of the decimal point there, it could be anything from 0 to 4. So when we see this written this way and we know it was rounded to 3 significant digits, we know it could be it could have came from any one of these numbers. But as you can see, this is every one of these is a little closer to 540 than these are. Over here we rounded to 2 significant figures. Our other possibilities, other than 540 exactly, we're all at least 1 away from 540. Over here where we round to 3 significant digits, our other possibilities other than 540.0 exactly were no more than 0.4 away from 540. So we get a little more meaning in our number by putting more significant digits into our number. And we can think of accuracy as the number of significant digits that we have in our number. And then we just talked about that. We got more meaning when we had more significant digits. It's kind of confusing to think that accuracy is the number of significant digits, because you might think it was if the number was correct, whether there was error or not. But if your number that you've written down is 74.3, 3 significant digits there, and if you had a better reading, it was actually 77.0, but we have some error here. But a lot of times we think of that as accuracy, but when we're trying to talk about accuracy for the context of what we're doing right now, we're thinking of the number of significant digits. More significant digits is a more accurate number. Now precision is kind of similar, but precision is based on the last digit. 74.320 is more precise than 74.32 or 74.3, even they all round that way, or even 74. The more digits we carried out, the more precise, which basically means if we had a number line, that number's somewhere on the number line, the more digits we have, the more closely we can place our number to what you might call the target number. It's more precise is how far away it is here, and more digits is basically how many points you divide the thing up into. If you think about, let's try this. Suppose we got 12. Well, that's two significant digits. What's the biggest number we can get with two significant digits? 99. So if we have two significant digits, we could divide this up into 99, whatever thing we're measuring, we could divide it into 99 possibilities. But if we have 12.001, we know that whichever one of these we choose, we're within 1/1000th of the actual number. Where the precision allows us to dial in more precisely, where the number of significant digits gives us more choices. So it's a little bit, that's the accuracy versus precision. It's kind of, can be kind of confusing to think about, but now, the result of a calculation can never be more accurate than the least accurate measurement. Let's say that we measure voltage across a certain point in the circuit, and we measure it we measure voltage, three different voltages in a circuit. We want to add them together. Suppose we measure 3.1 volts, 2.2 volts, and 1.75 volts. And maybe these were all in series, so they're going to add up to some total voltage. Well, here we have a meter, a measurement that read to 1/10 of a volt, 2/10 of a volt, or to, again, tenths column, the tenths of volts. This one reads to hundredths of volts. This seems to be more accurate. So let's add these together. 2.2 volts, 1.75 volts, 5, 0, carry the 1, and we get 7, right? We get 7.05 volts. Now, this three significant digits and this second decimal place of precision implies greater accuracy than we really had. So our lowest accurate number only had two significant digits. So we have to round this to two significant digits. So we're going to use this squiggly approximately equal. So we're going to be interested in rounding that guy right there, that second digit. 7 point, that's a 0. The number to the right of it is a 5. Remember, we looked at our rules a little bit ago. If the number is 5 through 9, we increase this guy by 1. So that actually rounds to 7.1 volts. So after we get, but we do that after we did our calculation. We don't want to drop. What if we did this first and made this to be, oh, okay, let's round that to 1.8. Let's see what we got. It might give us the same number, but 2.2, 1.8, 10, 1, carry the 1. Yeah, in this case we got the same answer, but when you get a bunch of those, it may not always come out the same. You don't want to get rid of this portion of the accuracy until you're all done doing the addition. We're going to do another example kind of like that. Measuring the current in a circuit. I'm going to measure this at 3 different times. First measurement, we get 15 milliamps. Well, let's get the second measurement, we get 11.5 milliamps. Time went by. Apparently the current changed a little bit. Third measurement, we get 10 milliamps. Now, we want to find the average of those. And we want to add them up and divide it by 3. So 15, 11.5, 10, 5, 6. So this comes to 46.5, the total. We want to divide that by 3 because it's going to be 15 milliamps plus 11.5 milliamps plus 10 milliamps over the total number of readings, which was 3. This is for the average. For the average, we sum up the readings, divide by the number of readings. So we did the 15, did we add these up right? 5, 6, oh excuse me, that's 36.5, right? Yeah, there was no carryover. That's 36.5. Now we want to divide that 36.5 by 3. We'll divide the 3. 3 into 3 is 1. Subtract the 3, that leaves the 6.5 down here. 3 into 6 is 2. And 2, 6, subtract again. We have the 5. 3 into 5. Carry up the decimal point is 1. Subtract the 3. We got 2. 3 into 20 gives the 6. So now we're gonna get this 6-bar repeating thing. We're gonna keep getting the 6s all the way because it's repeated once. Now we want to round this so it's no more precise than our least precise number. Well, our least precise numbers were these two, which had no fractional part. They were whole numbers of milliamps. So we want to take this 12.166 average, and we want to round that to 2 significant figures. Well, it's 1. The second figure is the one we're rounding to. We look to the right. We got a 1, so we don't do anything. So that average rounds to 12 milliamps. If we kept this more digits, that would be implying we knew it was here and knew it was here. And this could be 15.0, this could be 10.4, and many other choices. This number could be anything 0 through 4, this could be 0 through 4. So we don't know enough about that 10th place, the place to the right of the decimal point, to make any claims about it in our answer. And that's why we calculated it, we used all the information that we had, then we rounded to a number that had no more significant digits than our least number of significant digits in the data we used to calculate the answer. Anyway, I think that kind of covers it for today. Be sure to like and subscribe, and until the next time, keep on learning.